Hello everyone, this video will be a walkthrough of the end of the packet that we didn't quite get to in class. So we're going to start near the end of the packet where we're talking about calculating matrix inverses. So at the end of class we talked about the two different ways we would calculate a matrix inverse. One, we have a formula, and remember this formula only works for 2 by 2 matrices. And we have a general process where we would take the matrix, we would augment with the identity matrix, we would do that row reduction process, and if A is invertible, the left-hand side would row reduce to identity, and the right-hand side would gather up all our row operations and turn into A inverse. Let's see both of those guys in action. All right, so I have three matrices here, and in class this would have been a learning catalyst question to calculate the inverses if they exist. So I would encourage you to pause and give it a try. And now that you've worked through them, you can verify your answers as I work through mine. Here's my matrix A. It's a 2 by 2, so I'll use my formula. A inverse will be 1 over this product, 2 times 1, minus that product, 2 times 0, times the matrix I get when I switch the values on the strong diagonal and I change the signs on the off diagonal. So once I kind of write that description out, I can then simplify. This coefficient is 1/2. If I multiply each of the components by 1/2, I get 1, -1, 0, and 1/2. And this would be my inverse. Now remember, I can always check to make sure that's correct when I'm done by taking my inverse and multiplying it by A. If I multiply these two guys together, I should get to the identity matrix. If I take that times this, I'm going to get 1 plus 0. If I take it times the second row, I'm going to get 0 plus 0. Then over here, I'm going to get 2 minus 2, and 0 plus 2 times 1/2, which is 1. Sure enough, I get identity. All right, so that's a quick little check I can do on the exam to make sure that I haven't screwed up. Next, I get to this matrix over here. This matrix is a 2 by 3 matrix, which tells me right away it's not invertible. Only square matrices can possibly be invertible. They're not all invertible, but the only way they possibly could be invertible is if they are square. All right. Next, I have a 3 by 3 matrix. So if I wanted to invert this one, I would take my matrix and I would augment with the identity matrix, and then I would do row reduction like normal. So this row reduction means I want to put a 0 in this position right here. So to do that, I would take row 3 plus row 1. Row 1 would stay the same, row 2 would stay the same. My new row 3 would be 0, 2, 1, 1, 0, 1. If I took the third row plus the first row. Now I need to get a 0 in this position, so my next row operation would be row 3 minus 2 times row 1. I'm going to use my second pivot to get a 0 below it. Row 1 stays the same, row 2 stays the same, row 3 becomes 0, 0, 1, 1, and 0 minus 2 times 1 is -2, and then 1. I'm almost done. Now I just have to get a 0 in this position. So to do that, I'm going to have to modify row 1. I'm going to take row 1 minus 2 times row 2. This time row 3 stays the same, and row 2 stays the same. My new row 1 is 1, 0, and 0. 1 minus 2 times 0 is 1. 1 minus 2 times 1 is -2, and 0. So the left-hand side is reduced to identity, and the left-hand side should be my inverse matrix. So my inverse should be equal to 1, -2, 0, 0, 1, 0, 1, -2, 1. And once again, if I had time on the exam, I could always multiply that by A to see if I get identity or not. So there's my inverse. Next question is use the inverse. Given that matrix and some vector b, I want to solve ax equals b. And on the exam, it might be even more explicit. It might say use the inverse to solve. And if that's the case, then, well, I could just multiply both sides of my equation by my inverse matrix, like that. Inverse times a is just identity, and identity times x is just x, which really shows me that my solution to this matrix equation is just going to be the inverse times b. So for this problem, all I need to do is take my inverse, which I've already calculated, and multiply it times b. All right, when I do that, I'm basically adding the first and second columns. That's what multiplying by 1, 1, 0 will do. So I'll get negative 1, 1, and negative 1 here. There's my solution. And of course, this is the x, my solution. And if I multiplied a times x, I could verify that it gave me b. That would be another way to check my work. Now, on the exam, you might see this question as, given the matrix A, find the inverse and use it to solve. If you screw up that process of generating the inverse and you know your answer is wrong, that's okay. Still clearly identify what A inverse is. Show me that you know you would solve it by taking A inverse times B, and you'll get some sort of partial credit. Okay? So even if you screw up the inverse calculation, show me you know what to do with the inverse. All right. That wrapped up 2.3. From there, we launched into 2.8 and 2.9, where we talked about vector spaces. We began this process of generalizing the concept of vector space. A vector space could be more just the R2 and R3 spaces that we've been working with, but instead it could be any group of objects with definitions for vector addition and scalar multiplication that satisfied our properties. We basically had two different groups of properties. We had additive properties, and we had multiplicative properties. And in general, we'd have to take our collection of objects, our definition of addition and scalar multiplication, and prove all 10 of these were satisfied to show something was a vector space. However, if we knew that we had this big vector space and we had a sub-collection of objects inside of it, and we wanted to show that that subset was actually a subspace, we wouldn't have to check all 10 properties. In fact, we'd only have to check 3 properties: closure under addition, closure under scalar multiplication, and that 0 was in the set. We can summarize that below here. A subset of elements from a vector space can be a vector space by itself. We call this subset a subspace. To show that a subset is a subspace, we don't have to verify each of the properties, but rather just these 3 properties. Okay. Now let's see if we can apply this. The set of all continuous functions is a vector space. What are continuous functions? Well, sine of x is a continuous function. E to the x is a continuous function. X cubed minus 2x plus 4 is a continuous function. We have all these functions, they're all continuous functions, and if I look at the set of all possible continuous functions, they actually forms a vector space. You don't have to show that, I am telling you that. But if that's our big giant space here, continuous functions, then the set of all polynomials of degree 2 or less, well, that lives in here somewhere. Now the question is that subset of content, is it actually a vector space? Well, the set of all polynomials of degree 2 or less would look like this: ax squared plus bxc for some real numbers a, b, and c. So now we have to show that this satisfies the properties. So 1 is 0 in our set that I'll call little v here. So we're going to give v our set. Well, if I let a, b, and c equal 0, I would have this guy, which is equal to 0. If I add that value to any other polynomial, does it change the value of the polynomial? It does not. So 0 is in the set. Next, what about closure under scalar addition and multiplication? Well, the idea is if I take my polynomial and I take any other generic polynomial, so this was ABC here, I could go dx squared ex and plus f, and I add them together. How do I add polynomials? Well, I'd have a plus d times x squared, I'd have b plus e times x, and I'd have c plus f. In other words, some number times x squared plus some number times x plus some number. If I add any two polynomials of degree 2 or less, I get a polynomial of degree 2 or less. So it is closed under vector addition, and you can imagine that if I took this whole thing and I multiplied it by 200, it's still going to be a polynomial of degree 2 or less. So it's closed under scalar multiplication as well. So this set of all polynomials of degree 2 or less is actually a vector space by itself. That means if it's a vector space, we can talk about this vector space in terms of vector space vocabulary, such as basis. What is a basis? It's a set of linearly independent vectors that span a space. Okay, so there's two sub-vocab words in our definition of basis. Okay? To span a space, what does that mean? Spanning space means that the set of all linear combinations includes every vector in the space. If I have two vectors that span R2, it means I can take a linear combination of those two vectors and build any vector in R2. So this means that I can build any vector in the space using my basis vectors. What about linearly independent? Well, that means that none of the vectors can be written as linear combinations of the other vectors. I don't have any extra vectors, any repeated vectors, right? So in other words, if I had these three vectors and said, is that a basis for R2? They certainly span R2, but this one is just a linear combination of the other two. So that wouldn't be a basis. I'd have to eliminate that vector before I had a basis. Okay? A basis must be linearly independent and span the space. The heuristic summary here is a base is the smallest set of vectors I can build the entire space with. And that also gives us the idea of dimension. Dimension is the number of vectors in a basis, and in some sense is how I can talk about the size of a vector space. So R2 is a two-dimensional space because there are two vectors in its basis. All right, let's go back to our vector space now, the set of all polynomials of degree 2 or less. The next learning catalytics question would have been, does this set of vectors form a basis? So in this space, 1 is a vector. 1 is a polynomial of degree 2 or less. X minus 1 is a polynomial of degree 2 or less. So each one of these four pieces here is a vector in this vector space. But do this set of four vectors form a basis for V? Feel free to pause this, think about it for a while. Hopefully you've thought about it and you can unpause it. And the answer is no, they don't form a basis. Well, why not? Well, I can imagine that if I took some number of this guy plus some number of that guy plus some number of this guy, I could actually generate 2x squared plus 1. Right? So if I gave these guys names, say B1, B2, B3, and B4, B4 would actually just be B3 plus, well, actually just B3 plus B1 in fact, right? So this guy is just a linear combination of the first one and the third one, right? So these four vectors are not linearly independent. They would not form a basis. However, if I got rid of that vector and just looked at these three vectors, it actually would form a basis, right? So we're going to let beta be the set of vectors 1, x minus 1, and 2x squared. These would be a basis for our vector space. If they're a basis, what would the dimension of our vector space be then? Well, there's three vectors in our basis, so the dimension of V would equal to 3. Now, this vector, 4x squared plus x plus 3, is an element of our vector space. It's a polynomial of degree 2 or less. That means I should be able to build it by using my basis vectors. So once again, I got a B1, I got a B2, and a B3. Now, because I'm dealing in an abstract space and not one of the R spaces, I can't systematically solve this through some sort of row reduction process. I kind of got to just ration it out. So I need to get a 4x squared term, right? That means I'm going to need two of my B3 vectors, right? Two of my B3 vectors. That would give me 4x squared. I'm going to need one factor of x. This is where I get my factor of x's from B2. So I'm going to need one factor of B2. Now when I do that, that means I'll have a x minus 1. I need to get my constants down to a value of 3, which means I'm going to have to add 4 of the B1s. And the result will be this vector v that I'm looking for, 4x squared plus x plus 3. So I can form this vector as a linear combination of the basis vectors. Now I'm going to rearrange these so they go from B1, B2, and B3. And that tells me that the coordinates of v with respect to my beta basis would be the vector 4, 1, 2. These are the coordinates of v in terms of my basis. Remember, the coordinates are how much of each basis vector do you need to form the vector. And this way I can kind of represent any polynomial with this little point here in R3. All right. Next, we'll look at some other vector spaces. Does a set of all solutions to this matrix equation form a vector space? Well, the answer is absolutely no. For instance, if I just plugged in 0, 0, 0, 0, that would not be a solution. So because 0 is not in the set of all solutions, automatically not a subspace. However, if I looked at the solutions to this equation, the homogeneous equation, it actually would be a vector space. 0 is in the space, and I could show that if I grabbed any two solutions, it would also be a solution. In fact, this vector space is actually a special vector space, which we call the null space. So the null space is a set of all solutions to ax equals 0. That should be a vector, and that should be a vector. It's all the x's that map to 0. The column space is a set of all linear combinations of the columns of A. If I took A and I multiplied it by X, well, one way I can do that multiplication is the linear combination process, which means the B's that I could generate through multiplication would all be linear combinations of the columns. So in some sense, the column space is the set of all B's that I can generate, and the null space is a set of all X's that map to 0, which means that the null space is going to be a subspace of the domain, and the column space of A is going to be a subset of the codomain. In fact, by definition, the column space of A is actually equal to the range of A. It's just another name for the range. Looking at an example here, I know that these are subspaces, but to call them subspaces means I need to show that they live in a larger vector space, and all these will live in larger R spaces. So if I have this specific matrix M, for instance, just for me to take this M and multiply it by some vector X, X would have to be a 6-dimensional object just for me to be able to do the multiplication. And if I put some value in here and actually did multiply them, get rid of my scribble there, the result would be a B1, B2, and B3. The output would be a vector in R3, which means multiplication of this matrix is taking vectors from R6 and mapping them to vectors in R3. The column space is where the B's live, so the column space would be a subspace of R3. The null space is the X's that map to 0. That has to be a subset of R6. And then lastly, we want to be able to take their definitions and answer all the other vector space questions about them. We want to be able to generate a basis, talk about their dimension, those kind of things. So in this case, in this specific example, we're given a matrix, and we are told that it row reduces to this nice form. And that actually will help us answer these questions more quickly. This would be another great spot to pause the video and see if you can answer these questions by yourself. Hopefully you've paused. This would be the next learning catalytics question, and work through this. And now you can see if your answers match mine. So the column space is going to be a subspace of R2, because if we take a linear combination of these columns, which are all vectors in R2, the result will be a vector in R2. And the null space would be a subspace of R4, because if we took that A, which is 2 by 4, and multiplied by X, X would have to be in R4. Now a basis for the column space. Well, I know that if I took linear combinations of these columns, it would generate the column space. So those 4 columns span the column space, but a basis must also be linearly independent. So what I need are the linearly independent columns of A. Now to find which of them are linearly independent and which are dependent, I would do the row reduction and identify where the pivots are. The pivots are in the first and third columns, which means I should take my first and third vectors of A to be the column space basis. The basis would be 1, 1 and 1, 2. Now once I've established a basis, that would also help me answer other questions. In this case, the dimension of the column space, which we also call the rank of A, would be equal to 2. And then lastly, we want to find a basis for the null space. Remember, the null space are the solutions to AX equals 0. So then to find a basis, I would solve AX equals 0, which means I would take my original matrix A, I would augment with 0, 0, and do the row reduction. Now in this case, the augmented column wouldn't change at all, and so I would be left with this result. From there, I would write out the associated equations. Minus 2x2, and I subtract that to the other side, minus x4. x2 is free. x3 is equal to negative x4. x4 is free. And then if I wrote my solution in parametric vector form, I would have x2 stuff and x4 stuff. Coefficients of x2 would be negative 2, 1, 0, and 0. Coefficients of x4 would be negative 1, 0, negative 1, and 1. So I could form the entire null space using a linear combination of those two linearly independent vectors. Therefore, the basis for the null space would be those two vectors. Once I have a basis, I can see that the dimension of the null space would be 2. So, having learned everything I did about vector spaces, how to generate a basis, talk about their dimension, I can then apply all that knowledge to the column space and the null space to special subspaces that are associated with the matrix A. All right, and that really wraps up this portion. The last little comment here was just a tease towards the next half of the semester that the concept of null space, i.e. the solutions to the homogeneous equations for a vector space, a form of vector space, is a fundamental concept of differential equations, which we will see down the road. But for now, these are the questions you will see on the upcoming midterm. All right, thank you for your time.